MISSE, or Materials on the International Space Station Experiment, is a suite of experiments that has taken hundreds of material samples and exposed them to the microgravity environment of space by being attached to the outside of the space station, some for a year, some for more. Richard Grugel is a materials scientist that had some samples fly on MISSE 8. Richard, tell us about MISSE 8 and the samples that you flew.
Well, thank you, Lori. Yes, we were fortunate enough to have several samples flying on the MISSE. Primarily, we have these ionic liquid epoxy samples, and this is the one that was up on the space station for over 2 years, 2 months. We brought it back, and we found that there was no obvious cracking, no delamination.
So it worked like you wanted to do?
Yes, it stuck to the aluminum substrate, and best of all, it didn't lose any weight in that environment.
Let's go back a minute and say, what are ionic liquids?
Okay. Ionic liquids are a novel class of materials probably discovered 100 years ago. For instance, if you take table salt and melt it at 1400 degrees Fahrenheit, you end up with an inorganic ionic liquid. Ours are organic ionic liquids, so they're liquid at room temperature, and they have a number of interesting properties, two of which are that they have extremely low vapor pressures, meaning they won't evaporate, and the second one is that they will conduct electricity at room temperature, which can lead to a number of interesting applications.
So all of the properties that it can extract, that's why you study it, right?
Yeah, we found that it's well survived the space environment, but it has other interesting properties too. For instance, when we cool it down, it doesn't really shrink a whole lot, which means we can probably apply it to making carbon fiber composite tanks. And this would be an example of one here, where we have a aluminum liner, much like a fancy soda can, that we wrapped with our epoxy and the carbon fiber.
It's a glue that holds this tank together.
Yeah, and the strength is given by the fibers, but the epoxy holds it all together. So,
and you can tell all that from that tiny little sample that
well, that helped us there, but we're going to do some more testing. For instance, we're going to shortly put these into a liquid nitrogen environment, submerge them in there, and test them to failure. And we're hopefully that this will work nice. Here's one without a liner that we made. This is a section from it, and we've tossed these into liquid nitrogen, corrosive liquid oxygen, and very cold liquid hydrogen. And of course, the liquid hydrogen and the liquid oxygen are the fuels that power a lot of the rockets that we use. And when we took these out and put them under our high-powered microscopes, we saw no cracking, no delamination, and it came out as it went in. So hopefully down the road,
on a journey to an asteroid or Mars, that's going to come in handy.
Yeah, we're going to get an opportunity to, hopefully we'll get an opportunity to make some composite cryo tanks without the aluminum liner, which will save a lot of weight, which is what we're all looking for. If we can just mitigate the micro cracking and the leaking.
All right, Richard, that's cool. So that's just one type of ionic liquid. I'm told there are several. Laurel Karr has been studying the uses of ionic liquids for 10 years or better, right, Laurel?
That's
tell
right,
us,
Laurel.
Tell us, now that you have all this information from the MISSE research, what are you doing with it?
All right. Well, the MISSE experiment demonstrated that the ionic liquids can be used in microgravity environment under very high vacuum conditions and with very large fluctuations in temperature. And so what we're doing here at Marshall Space Flight Center is we've used, you can make all sorts of ionic liquids. You can make them acidic, you can make them basic, you can use them as solvents, as cleaners, just all sorts of use, and ionic liquid of epoxies, of course. Right. But there's just all sorts of uses for them. Anything that you can do with a conventional chemical, you can usually do with an ionic liquid, and it's much more environmentally friendly. There's no vapor pressure, so there's no fumes. And it's done at a lower temperature, so it's very energy efficient.
And it's recyclable, too.
And it's recyclable, yes it is.
So tell us some of the things, how you have used this to study. You have a meteorite there, I think?
I do. This is a meteorite. It's an iron-nickel meteorite, and it's 92% iron and about 8% nickel. And we have used one that looks very similar to that and been able to extract iron and nickel from it and plate them out sequentially. This is the iron and nickel after it's been electroplated, all mixed together. But you could do it sequentially by varying the voltage. The nickel is plated here onto a copper electrode. This is a puck used in the Bosch reaction for separating, breaking down carbon dioxide into carbon and oxygen, and so that the astronauts can use that oxygen and the carbon can be taken off of the puck. What happens is during this process, this puck gets all covered with carbon and eventually it stops working. So if we use the acidic ionic liquid and take the iron off and get rid of the carbon and then replate another puck with the iron. So you don't have to take all the catalysts with you to replenish it.
So you're saying if we have a toolbox full of ionic liquids and some electricity, then this is really going to help us as we journey to an asteroid or Mars. We can use a lot of things that are already there.
That's correct.
And you can use this to make water, or water has to already be there?
The water has to already be there. If the water is in the lunar regolith, you can it gets brought up at the same time you dissolve the regolith with the acidic ionic liquid, and if there's metal oxides in the soil, like the moon has 40% oxygen within the regolith, and you can get that oxygen out because the hydrogen from the acidic ionic liquid mixes with the oxygen from the metal oxides and produces water. So this is water from a meteorite that was which meteoritists say was from the asteroid Vesta.
Is that really water? It's a drop of water.
Yes, it's really water. We had quite a bit more of it, but we had to use it as to analyze it to make sure that it was only water in there, and it was. It's essentially a distillation process, so it's very pure. And if there were enough to drink, you could actually drink it.
Wow, ionic liquids. Who knew there was ever so much to know about ionic liquids? I should have paid more attention in chemistry class.